Assalamualaikum and hi everyone. 2.3 application. So at the end of this subtopic, students should be able to solve problem involving first order differential equations. In this lecture 2, we will see the applications of differential equation. Now we will apply the method in this section to the solution of some practical situation. First, we look at the population growth model. The simplest growth model has a constant relative growth rate. If we denote the population, we are considering by y of t, then the rate of change of the population is dy over dt. To say that the rate of change is proportional to the population is just saying that there is a constant of proportionality of k such that dy dt equals to ky. Since k is a constant, this can be immediately separated to have 1 over y dy dt equals to k. And then integrate both sides with respect to t to have integration of 1 over y dy equals to integrate of k respect to dt. So we have ln y equals to kt plus c as a result of integration. Then by taking exponent of both sides, so we have y equals to e power of kt plus c. And we separate the index, so we have e power of kt times e power of c. And by substitute e power of c as a, so we have the equation of population growth as y equals to a e power of kt, where a is e power of c. The example of population growth is on example 9. In a particular bacteria culture, the rate of increase of bacteria is proportional to the number of bacteria n present at any time t hours after the experiment. Given that the number of bacteria at the beginning is 10 power of 6 and after 1 hour is 10 power of 9, find a the number of bacteria after 5 hours. Before we can answer the question A, we need to find the particular equation for the population growth. As the population is proportional to the number of bacteria, then we have dn over dt is equals to kn. Then by using the separable of variable, so we have 1 over n dn equals to k dt. And then by integrate both sides, so we're going to have ln n equals to kt plus c. And by taking exponent of both sides, so we have n equals to e power of kt plus c. And we can simplify as a e power of kt, where a is e power of c. So we have the general equations of the population growth. So in order to complete the equation, we need to find the value of a and the value of k. So we took the first value, which is when t equals to 0, we have n as 10 power of 6. Then we substitute into the equation. So we have 10 power of 6 equals to a e power of k times 0. So we have a as 10 power of 6. So our equation would be n equals to 10 power of 6 e k t. In order to find the value of k, we substitute the second value, which is when t equals to 1 hour, the population of n is equals to 10 power of 9. Then we substitute in the equation, so we have 10 power of 9 equals to 10 power of 6 e power of k times 1. So 10 power of 9 divided by 10 power of 6 equals to e power of k. So we have e power of k equals to 10 power of 3. And then by taking ln of both sides, so we have k equals to ln 10 power of 3. So we have k as 6.91. Then we substitute back the value of k into the equation. So we have n of t is equals to 10 power of 6 e power of 6.91 t as the particular solution for the population of the bacteria. So for question A, we want to find the number of bacteria after 5 hours. So when t equals to 5 hours, we substitute t into the equation, so we have n equals to 10 power of 6 times e power of 6.91 times 5, and we calculate the value, so we have 10 power of 21. And that is the population of bacteria after 5 hours. And for question B, find the time taken for the number of bacteria to be 3 times the original. So as we know, the original is when t equals to 0, which is n equals to 10 power of 6. So we have 3 times 10 power of 6 equals to 10 power of 6 e power of 6.91 t. And as we bring 10 power 6 over here, so we left 3 equals to e power of 6.91 t. And then by taking ln of both sides, so we have 6.91 t is equals to ln 3. So t is ln 3 divided by 6.91, and the value of t is 0.52 hours. So this means that after 0.52 hours, the population becomes 3 times the number of bacteria. Now we look at the applications of differential equation in radioactive decay models. Radioactive decay models, on the other hand, are very accurate over long periods of time. They are the primary method to determining age of prehistoric fossil and ancient artifact. If we denote the decay we are considering by C of t, then the decreasing rate of the decay is dc over dt. To say that the decreasing rate is proportional to the decay is just saying that there is a constant of proportionality k such that dc over dt equals to negative kc. Since k is a constant, this can be immediately separated as 1 over c dc over dt equals to negative k. And then we can integrate as integrations of 1 over c respect to dc equals to negative of integration k dt. So the integration we have ln c equals to negative kt plus c, and by taking exponent of both sides, so we have c equals to e power of negative kt plus c. By separate the index, so we have e power of negative kt times e power of c. So at the end we have the equation for radioactive decay as c equals to a e power of negative kt, where a is e power of c. Okay, now we look at example 10. Radium decomposed at a rate which is proportional to the amount present at any time. If 10% decompose in 200 years, what percentage of the original amount of radium will remain after 1000 years? Okay, first we let the rate of radium decompose as dr over dt equals to negative k r, and then we bring r to the left, so we have 1 over r respect to dr equals to negative k dt. And then we integrate both sides, so we're gonna have ln r equals to negative kt plus c, and then by taking exponent of both sides, so we have r equals to e power of negative kt plus c, and then by separating the index, so we have a e power of negative kt, where a is e power of c. So we have the general equations of the radium decomposed. Then in order to complete the equation, so we substitute the initial value, which is when t equals to 0, let the radium equals to R naught. So we have R naught equals to AE power of negative k times 0, and then we have A as R naught. Then the equation including A is R equals to R naught e power of negative kt. Okay, next we substitute the given value, which is when t is equals to 200 years, the amount of radium is decreased by 10%. We left as 90% or 0.9 of the original. So we substitute in the equation, so we have 0.9 of the original is equals to R naught e power of negative k times 200. So we simplify as 0.9 equals to e power of negative 200k, and by taking ln of both sides, we have a negative 200k is equals to ln 0.9. So we have k as ln 0.9 divided by negative 200, and we have k as 5.3 times 10 power of negative 4. So we have a particular solution for the radium, which is R of t is equals to R naught e power of negative 5.3 times 10 power of negative 4 t. So after 1000 years, R is equals to R naught times e power of, we substitute the value of t of 1000. So we're gonna have 0.6 of the R naught. That means 60% of radium is remain after 1000 years. Okay, now we look at the Newton's law of cooling. When an object has a temperature greater than the ambient temperature, it cools according to the Newton's law of cooling, which states that the rate of cooling is proportional to the difference in temperature, that is d theta over dt equals to negative k theta minus a, where the theta is the temperature of the object at any time t, and A is the ambient temperature. The solution to this separable differential equation is, we have integrations of 1 over theta minus A is equals to integrations of negative k. And from the integration, we have ln theta minus A equals to negative kt plus c. So by taking exponent of both sides, we have e power of negative kt plus c is equals to theta minus a. Then by bring a to the other side, so we left theta as e power of negative kt plus c plus a. And we can simplify as theta equals to e power of negative kt plus a, where a is equals to e power of c. Now let's see the application in example 11. A body temperature is 180 degrees Celsius, is cooled by immersing in a liquid at 60 degrees Celsius. In 1 minute, the temperature of the body has fallen to 120 degrees Celsius. So how long will it take for the temperature of the body to fall to 90 degrees Celsius? So we're gonna use the Newton's law of cooling with ambient temperature is at 60 degrees Celsius. From Newton's law of cooling, we have d theta over dt equals to negative k theta minus 60 degrees. Then we bring theta minus 60 to the other side. and we left negative k dt, and then we integrate both sides. So we're gonna have ln theta minus 60 is equals to negative kt plus c. Then by taking exponent to the both sides, so we have theta minus 60 as e power of negative kt plus c, and then by separate the index, so we have a e negative kt, where a is e power of c, and we have the equation of theta as a e power of negative kt plus 60 degrees. Then we substitute the given value, which is at t equals to 0. The temperature is 180. So we have 180 equals to a e power of negative k times 0 plus 60, and we have a as 180 minus 60, so we have 120 degrees for a. So we have theta as 120 e power of negative kt plus 60. And for the second value at t equals to 1, the temperature is 120. So we have 120 degrees equals to 120 e power of negative k times 1 plus 60 degrees. So we bring 60 degrees to the other side, so we have 120 minus 60, then we have 60 equals to 120 e power of negative k. We divide 60 over 120 degrees, so we left with e power of negative k equals to 0.5, and by taking ln of both sides, we have negative k as ln 0.5, so we have k is equals to 0.69. Then by substitute the value of k, so we have theta as 120 e power of negative 0.69 T plus with the ambient temperature 60. So for theta equals to 90 degrees, so we have 90 degrees equals to 120 e power of negative 0.69 T plus 60. So 90 minus with 60, so we have 30 equals to 120 e negative 0.69 T. And we divide 30 over 120, so we have e power of negative 0.69 T is equals to or 0.25. And then by taking ln of both sides, we have negative 0.69 T is equals to ln 0.25. So we have t as ln 0.25 divided by negative of 0.69, and we have the value of t is equals to 2 minutes. Now we see the application of differential equation in electric circuits. An RL circuit is one with a constant resistance R and a constant inductance L. The electromotive force EMF, a resistor and inductor connected in series. The EMF source, which is usually battery or generator, supplies voltage that causes a current flow in the circuit. According to Kirchhoff's second law, if the closed circuit with time t equals to 0, then the applied electromotive force is equals to the sum of the voltage drop in the rest of the circuit. It can be shown that this implies that the current I of t that flows in the circuit at time t must satisfy the first order linear differential equation. So we have L di over dt plus Ri equals to E. Then we divide the differential equation with L, and we have di over dt plus R over L times I equals to E over L. P of t is equal R over L, a constant, and Q of t is E over L, also a constant. Then the simplest model of the amount of current I in a simple electric RL circuit is given by a linear first order differential equation of di over dt plus P of t I equals to Q of t, where I is amount of current and t is time. The usual solution to the differential equation is to use the integrating factor V of t. Now look at example 12. The basic equation governing the amount of current I in a simple RL circuit is given by di over dt plus 50I equals to 5. And when t equals to 0, I equals to 0, find the current at any time t. So we have the differential equation di over dt plus 50I equals to 5. So as we can see, this is a linear differential equation where P of t is equals to 50. Then we can directly find the integrating factor V of t as e power of integrate 50 respect to dt. So we have here e power of 50 t as the integrating factor. Then we multiply both sides with V of t. So we have e power of 50t times di over dt plus 50I on the left side is equals to e power of 50t times on the right side is 5. So on the left we have differentiations of dt of e power of 50 t times I equals to 5 e power of 50t. Then by integrating both sides, we have e power of 50 t times I, and on the right we have integrate 5 e power of 50 t respect to dt. So we integrate and have e power of 50t over 10 plus c. So by bringing e power 50t to the right, so we're gonna left I of t as 1 over 10 plus c e power of negative 50t. So we continue on the side. As the given initial value for t equals to 0, we have I is also equals to 0, and we substitute on the both sides, so we have 0 is equals to 1 over 10 plus c times e power of negative 50 times 0. So we have c as negative 1 over 10, and then we substitute back c into the general solution. So we have I of t is 1 over 10 minus 1 over 10 e power of negative 50t, or we can simplify more as we factorize 1 over 10 to have 1 minus e power of negative 50t. So this is a particular solution for the electric circuit. That's the end of chapter 2. Thank you and goodbye.